Unit 5, Day 3, Optimum surface area and volume of a square-based prism. So recall that the optimum rectangle is the square. And last lesson we used this to develop the formula for a cylinder. So today we will investigate the formulas for a square-based prism. So just like we did for the cylinder, let's look at this question here. In order to have an optimum rectangle, i.e. a square, what needs to be true about the dimensions? So we learned from above that for an optimal rectangle, it needs to be a square such that the height is equal to the side. So both those lengths are the same. So knowing this, we can now derive the minimum surface area and maximum volume equations, just like we did for the cylinder. So just like before, to derive the formula for the minimum surface area, we'll start with the regular surface area equation, but then put in our restriction that the height has to equal the side lengths. So recall from before that the surface area of a square-based prism is equal to 2 areas of the squares, which are the faces, plus the 4 areas of the rectangles that make up the sides. Now we know that the area of a square is equal to side length squared plus 4, the area of a rectangle usually is just length times width. Now here's where we plug in that restriction. So we learned before that the length has to equal the width, or the side has to equal the height. Let's plug that in. So instead of writing length times width, I'm going to write side length times side length, meaning they're the exact same length. And that becomes s squared. Now, because these are like terms, we can add them together to get the final optimum formula for surface area of a square-based prism is 6s squared. Let's now investigate the formula for the maximum volume of a square-based prism. Usually, it would be volume of a square-based prism is equal to the area of the base of that prism times the height of that prism. So volume is equal to the area of the base, which is a square, times the height of that prism. Now we implement our restriction. Height is equal to side length. So let's write s instead of h, because now we can combine these two terms and only have one variable. So s squared times s is s cubed, and therefore this is our formula for the maximum volume of a square-based prism. Let's now look at an example. Determine the maximum volume that can be held by a square-based prism with a surface area of 600 centimeters squared. So since we have a value for the surface area, let's plug that into our surface area formula from before, solve for s, the side length, and then we can use that side length to actually calculate the volume. The surface area formula for an optimal volume of a square-based prism is equal to 6s squared. Now let's plug in 600 for surface area and solve for s. So let's divide both sides by 6. That cancels out and we're left with 100 on the left side. Now to get s completely by itself, we need to get rid of that squared. So let's do the opposite. Take the square root of both sides. These guys cancel out. Square root of 100 is equal to 10. So therefore 10 centimeters is our side length. Now let's plug that into the volume formula to find the maximum volume. So our formula for the optimal or maximum volume, or maximum volume of a square-based prism is volume is equal to side length cubed. Now let's plug in our 10 centimeters for our side length, and we're left with 1,000 centimeters cubed. Therefore, the maximum volume that can be held by a square-based prism with the surface area of 600 centimeters squared is 1,000 centimeters cubed. So the first thing I want you to notice is that the volume here is given in milliliters. So let's convert that to centimeters cubed. So you have to know that 1 milliliter is equal to 1 centimeter cubed. So 125 milliliters is going to equal 125 centimeters cubed. So now let's proceed. We'll use our value of a volume, plug it into our volume optimal formula, to find our value of S, and then we'll plug that value of S into the surface area formula to find our minimum surface area. So let's begin. Here's the formula for the optimal volume, which is volume is equal to S cubed. Let's plug in our value of 125 for our volume. Now if we take the cubed root of both sides, these will cancel out, and we're left with 11.18 centimeters is equal to our side length. Now let's plug this side length into our surface area formula, and the optimal surface area formula is equal to 6s squared. And if you plug that into your calculator, you should get 749.95 centimeters squared. Therefore, the minimum surface area required for a square-based prism with the volume of 125 milliliters is 749.95 centimeters squared. The final example here is an application. So example 3, a cereal company decides to use a square-based prism packaging design. Each box is required to hold 3,600 milliliters of cereal. What is the minimum amount of cardboard required to contain the cereal? So they're essentially asking us what the minimum amount of surface area is to contain the cereal. First things first, this is in milliliters, so let's convert it to centimeters. So we know that 1 milliliter is equal to 1 centimeter cubed. Therefore, 3,600 milliliters is going to be equal to 3,600 centimeters cubed. And now, since we are given the volume, let's use our optimum volume formula, plug this value in, solve for the value of S, and then we can put that value of S into the surface area formula and actually find the minimum surface area value. So our volume formula is equal to S cubed. We can plug our volume value in, so the 3,600. Now let's take the cubed root of both sides to get rid of the cubed by the S, because that will cancel it out. And then we are left with 15.33 centimeters is equal to S. Now let's take that value for S and plug it into our optimum surface area formula to get the minimum amount of cardboard. So surface area is equal to 6s squared. Let's plug in our value for S. And if we plug that into our calculator, you'll get 1,410.05 centimeters squared. Notice I'm always rounding to 2 decimal places. Therefore, the minimum amount of cardboard required to contain this cereal is 1,410.05 centimeters squared.